Our next theorem will be on the transitivity of initial sigma algebras. So for this, let us consider index set I, non-empty, and another index set I sub small I, for all I in capital I. So again, here our non-empty index set is capital I, and we have another family of index sets I sub small I parameterized by the original index set capital I. To illustrate this, let's say, transitivity, suppose I have a set X, and this maps to Y sub I for a function, for some function F sub I. And then let's say this Y sub I is mapped to Gij. So I here is in capital I, and J is in I sub small I. And this maps to a double index set, let's say Z sub I J. And here we have a sigma algebra on Z sub ij. And here we can equip this Y sub I by the initial sigma algebra generated by this family of functions. Okay. So there are two ways to put a sigma algebra on X. That is, first, we consider the composition. So that's Gij followed by F sub I, and construct the sigma algebras generated by the composition. Or we can generate the initial algebra, initial sigma algebra generated by these functions based on this sigma algebra on each Y sub i's. And it turns out that even if you do this transition, you get the same sigma algebra. So to state that more precisely, so suppose that I have a family or a double index family of measurable spaces. For each I in the index set and J in the other index set I sub I. And also, so let us put it down. Put it here. So for each I in I and J in I sub I. And also I have this function T sub ij mapping Y sub I to Z sub ij. Okay. Now consider the measurable space Y sub I equipped with the initial sigma algebra obtained from these functions G sub ij. So again, recall that this is the initial sigma algebra generated by this family of functions. Then the initial sigma algebra generated by f sub i's, and of course this is true for all I and capital I, is the same as the sigma algebra generated by the compositions. So even you transition to y sub I, you get the same sigma algebra if you just merely take the composition. Okay. So for this, let's start with the proof. And again, to simplify notation, let us denote by E sub I to be the union of the inverse images of GIJs. This is for all I in the original index set. Okay, then we can say that, of course, by definition, that the sigma algebra of E sub I is the same as the initial sigma algebra generated by this family of functions. Okay, so from this, it follows that, okay, starting from the collection of, or the union of the inverse images of f sub i's of E sub I. So this is the same as, okay, applying the properties of inverse images, that is the inverse image of the union is the union of the inverse images. So we end up with the following. Here we utilize this equation. So you have F inverse of Gij inverse of Uij. However, take note that the sets involved in this double union can be written as the following. So this can be written as the inverse image of the composition. So therefore, this implies that the initial sigma algebra generated by the f sub i's by definition is the sigma algebra generated by the union of the inverse images of E sub i's. And this is the same as, okay, according to the above equation, this double union of inverse images of the composition. Okay, by definition of the initial sigma algebra, this is nothing but the sigma algebra generated by the compositions. And this is what we aim to show. So that's transitivity. So a consequence of this transitivity of initial sigma algebras will be the associativity of the product sigma algebra. So in other words, the grouping for the product sigma algebra is immaterial. So to state this more precisely, let us again take a non-empty index set and the index family of measurable spaces. Consider a partition, let's say I sub I, or I should say I sub j, j in capital J, of our index set. So here, this means that I sub j is non-empty for all j in capital J, another index set capital J, and I is the union. So this is what we meant by a partition. So we divide the index set I into a smaller collection of indices. Okay, so let us define the map, let's say I sub j. So this is a map from the product space, the Cartesian product of the Cartesian product. To the whole Cartesian product. So here we partitioned the Cartesian product into another Cartesian product. So the definition is simple. So you take the following function. So the function on the domain has the following form. So x sub k, k in I sub j, j in capital J. This is equal to x sub I. Then this map is projective. And you can easily verify this, and I will leave the details for you to check. Okay, so as an illustration, let us consider a finite set of indices, let's say 1, 2, 3, j consists of only 2 elements, so I sub 1, let's say this is what, 1, and I sub 2 to be 2, 3. So we partitioned I into 2 sets, I sub 1 and I sub 2. So the Cartesian product on the left can be written as follows. So first we have here x sub 1 cross. So here we are now using the usual notation for Cartesian products. Okay. And then x1 cross x2. On the other hand, the codomain or the range is equal to this one. And this should be corrected to 2 and 3. So technically, these sets are different. Okay. Theoretically, these are different. Why? Of course, this one, you can think of this as an ordered pair. Okay. Where the first component is only one element, consists of only one element, and the second is another ordered pair. Here, x sub k is in capital x sub k, k from 1 to 3. On the other hand, this is an ordered triple. So said theoretically, these sets are not the same because the first one consists of an ordered pair, where the second component is another ordered pair. On the other hand, the second set is an ordered triple. But of course, there's a one-to-one correspondence. Between these two sets, right? So you can easily check that this correspondence is bijective. So in this way, we can treat these sets to be quote-unquote equal via this one-to-one correspondence. Okay, so now we consider the identification so we identify this Cartesian product of Cartesian products with the whole Cartesian product. Well, technically this is equal, quote-unquote equal via the map ij. So we treat them as equal by identifying the corresponding elements between the two sets. So as I said, technically they are not equal, but we identify them via the map I sub j, by the bijection I sub j. So you can think of this as some sort of associativity up to bijection of Cartesian products. Okay, so now that we have this identification for J in capital J and I in I sub j, we now consider the projection maps Okay, so let us draw the corresponding diagram. So we have here the whole Cartesian product. We consider this projection pi hat j. So we project on the Cartesian product of sets having indices in capital Ij. And this is projected to x sub I. Let's say by this projection pi tilde ij. So what are the definitions of this projection? So pi hat j of this function is equal to xk k in ij, and pi tilde ij is equal to x sub I. And based on this, by definition, you can see immediately that the composition of these two projections is nothing but the projection on the ith coordinate. So that's a pi sub I. And this is true for any j in I sub I, and for all I in capital I. Okay, then the definition of the product sigma algebra tells us that this partial Cartesian product, or this partial product of sigma algebras, partial here means that we only take the product with respect to the smaller index set I sub j. This is the sigma algebra generated by the projection maps pi tilde ij, where I is in I sub j, for all j in capital G. Now, by transitivity of initial sigma algebras, okay, take note that here the composition is just pi sub I, but the projection maps pi sub I generates the whole sigma product sigma algebra. In that way, we can say that the product sigma algebras of this product sigma algebra is the same as the whole product sigma algebra. And this is your associativity of product sigma algebras. So one might ask about commutativity. Of course, this is also valid, and you will be asked in the exercises or in the next exercise that you show that the product sigma algebra is commutative at least for two sets. So another consequence of the transitivity for initial sigma algebras, this is related to measurability of functions, is the following corollary. So let us consider the following measurable spaces. And we have a family of functions. Okay. Say f sub I from x to y sub I. So to illustrate this, we have, let's say, suppose I have a function g from z to x, and this x is equipped with the sigma algebra, okay, or initial sigma algebra. This one is mapped to y sub I with the sigma algebra t sub I. And here we have the composition. So G followed by f sub I. Then the map G to Z. The map G is what? Of course, the sigma algebra on Z is U. So G is, let's say, U T sub I measurable. Here we are emphasizing the sigma algebras. So it should not be T sub I, but instead the initial sigma algebras or sigma algebra. If and only if the compositions is U T sub I, okay, measurable for all I in capital I. So measurability of a map from Z with the given sigma algebra into the initial sigma algebra is the same as the measurability of the composition of G and the functions that generate the sigma algebra. So we prove this. And suppose that, let's say, according to the definition of the initial sigma algebra, H f sub I is measurable with respect to these sigma algebras. More precisely, this is the remark I've mentioned, that the initial sigma algebra is the smallest sigma algebra wherein these functions f sub I are measurable. Here we only emphasize the sigma algebras involved for measurability. Okay, then the composition. Okay, so being a composition of measurable functions or measurable maps is also measurable. With respect to the pair, of course, U, T sub I. Okay, so we established this last time. For the other direction, now, so assuming that the compositions are measurable for each I, since, okay, if I take the inverse image of T sub I, this is a subset of U for I. This is nothing but the measurability of the composition. We have the following. So sigma of G is the same as a sigma of Fi OG I in a capital I. So this is according to the transitivity. And this is a subset of U according to this inclusion here. Okay. However, note that sigma of G by definition is G inverse of the sigma algebra corresponding to this. Okay, because this is the sigma algebra on X. So that, okay, the G inverse of this one is a subset of U, which implies, okay, the measurability of G with respect to the pair. We have the first one, the initial sigma algebra, and the sigma algebra U. It should be the other way around. So with respect to U and the initial sigma algebra. And this proves the reverse direction. Okay, a direct consequence of this theorem or corollary, if we replace, let's say, y sub I, t sub I by x sub I, sigma sub I, and we replace f sub I at the projection maps, then we have the following remark. So that z, u, and xi, sigma I the measurable spaces for all I in capital I. Then a map G from Z into the Cartesian product. This is U product sigma algebra measurable if and only if the composition of the projection maps, this is now a map from Z to X sub I, is U sigma sub I measurable. And this follows immediately from the previous corollary and the definition of the product sigma algebra. Let me discuss further topics. What if we have, instead of sigma algebra, we have more? So we have a topology, so that we get the Borel sigma algebras. So that would be the product Borel sigma algebras. So let me present two theorems without proofs, and the details, of course, are provided in the lecture notes. So let me discuss the contents of this theorem. So now we have an additional structure. So we have a topology. So let us consider an index family of topological spaces, all I, and let us equip the Cartesian product by the so-called Tikhonov topology. For those who are not familiar with the Tikhonov topology, can think of this as the smallest topology where the projection maps pi sub I. So this maps the Cartesian product onto the ith coordinate are continuous. For all I. Okay, so this is the Tikhonov topology. The smallest topology wherein the projection maps will be continuous. Then we can show that the product Borel sigma algebra, unfortunately, this is not equal to the Borel sigma algebra of the Cartesian product, but it is a subset. So once again, the product Borel sigma algebra is a subset of the Borel sigma algebra generated by the product topology or the Tikhonov topology. So these two are not equal. So we have only an inclusion. However, under the special case where our index set is countable and your topology can be generated by a countable basis, and that is the case, for instance, for Euclidean spaces, these two are equal. So let K be a countable set. It can be a finite set or a countably infinite set. And Suppose that our topological space x sub k, tau sub k has a countable basis. Well, this means that any open set can be written as a union of basis elements. Those who are not familiar, you can read a standard text in topology, for instance, of the book of Munkres. So if this is satisfied, then the countable product sigma algebra is the same as the Borel sigma algebra generated by the countable or the Tikhonov topology. Okay. So these two are equal if, again, your index set is countable and you have a countable basis for your topology. So as a particular example, let us consider a subset, x of Rn and y a subset of Rn. We know that Rn and Rm have countable basis. Okay. Namely, you take open balls where the center are all rational numbers and the radii are rational numbers as well. So that will generate the Euclidean topology or the usual topology. Okay, if we look at the restriction Borel sigma algebra, well, by definition, this is the Borel sigma algebra on the product topology x cross y. And according to the previous theorem, this is the same as the so this is for the right hand side, and the left hand side would be the following product sigma algebra, and we know that of course this is the restriction sigma algebra on x, Borel sigma algebra on x cross the restriction Borel sigma algebra on Rm on y. Okay, so the left hand sides are the same as our restriction Borel sigma algebras. So in particular, taking x to be the whole Euclidean space Rm and y to be the whole Euclidean space Rm, we now include the following. So the Borel sigma algebra on Rn by m, or n plus m, is the product sigma algebra of the Borel sets in Rn and Rm. So the Borel sets in the product space is the sigma algebra of the Borel sets. I would like to take note here that this cannot be extended to the case of Lebesgue measurable sets. And that's it for product sigma algebras. In the next lecture, we will consider these topics in constructing product measures.